I just want to point out that there was a sign error in the exercise I had given you. If you care to do it, you will find that this has to come with a plus sign. And before we get back to the orthogonal groups, I thought I will give you the definition of a group so that you can correlate with whatever things which you have seen. So, let us have only one definition for today. A group consists of two things, a set G and an operation which we will indicate with a dot, which is a composition rule. Okay, so, this is consists of a set, and let us just say that we will write elements G1, G2, G3, and this is the composition rule. A group consists of these two things, and a group G satisfies the following conditions. So, the first important thing is closure, which means if you take any two elements G1, G2, it belongs, the composition rule gives you another element of the set, and for all G1 and G2 belongs to G. So, this symbol stands for all. Okay. Second is the existence of an identity. Let us just call it identity. So, there is a special element. So, there exists an element, let us call it E, the identity, it is called the identity, satisfying for all G, for any G. Okay. And existence of an inverse. Okay. So, given for any element which belongs to this thing, there exists an element which we will call G inverse. There is just a symbol for it, such that the composition rule for G dot G inverse is equal to G inverse dot G equal to identity. Okay. So, I think if you want to be mathematically precise, I think it suffices to give one of these two conditions, but we will not get into such mathematical details. And the last one is associativity. So, the composition rule okay. So, if you are given a group, it is not enough to be given a set, because the operation is important, you need to check both of them. So, just to give you a counter example, Z, which is a set of integers with addition as the operation, is a group. You can check everything, and 0 is the but if you take the same set and change the operation into multiplication, you can check that closure works, identity also works, but one is the multiplicative identity, it is called. but something is violated, the inverse. Okay, you have to go outside the set of integers to define the inverse. So sometimes I guess this is called the monoid or something like that, where this particular axiom is violated, but this is not a group. But okay, then there are some more sort of if statements. You say a group is non-abelian if G1 dot G2 is not equal to G2 dot G1 generically. Okay. There could be a pair of elements which commute with each other, okay, but that what it means is that there exist such elements which do not commute, the order matters. G1 dot G2 is not equal to this. Coming to this group, the order does not matter, 3 plus 2 equal to 2 plus 3. Okay, such groups are called abelian groups. Okay, non-abelian means not abelian. Okay, so this group is abelian. So coming back to our example from last lecture, G would be the set of n by n orthogonal matrices, or D by D, right, is what I call it. And dot is equal to matrix multiplication. Okay. So the first thing which we did yesterday was to see that or maybe I left it as an exercise, is to show that the product of two orthogonal matrices is another orthogonal matrix. So that is the closure part. What is the identity? It is just the identity matrix. So closure works. What about identity element? E is nothing but the identity matrix, D by D identity matrix. Okay. Inverse obviously exists. So let us say that O is an orthogonal matrix, then we know it is easy to show that O inverse is nothing but O transpose, which is another orthogonal matrix. And associativity holds for all matrix multiplication, the order does not matter. Okay. So I will not check that part. So you can see that this group is it satisfies all the axioms of the group, and this, so we call this group O n, right. So then this is the group for which we use the symbol O n or O d rather, and if we put in an extra condition which is determinant being 1, that became the special orthogonal matrices. Okay. And is there anything else I want to say about this? Associativity is, I mean, it follows from associativity of matrix multiplication. Good. So now the question is the group abelian or non-abelian? So let us just choose SOD, and the question is the group abelian? Well, typically matrix multiplication does not commute, but there is an exception in this. SO2 is abelian, but generically if SOD for d greater than or equal to 3 is non-abelian. This is something we know. For instance, when we define Euler angles, every book has its convention, and they are not equal to each other because it matters. One will do, let us do a, so there is, for instance, they would say take first do a rotation about the z axis, followed by something about the y axis, followed by again the other z axis. Obviously, if you exchange the two, the second two things, you get you can combine the two the rotations about the z axis to make it into a single rotation about the z axis, and so then they obviously cannot be the same, and you know this. And SO2 being abelian just tells you that if you that is just a rotation about an axis, if you wish. If you rotate by some angle theta 1 and then follow it up with a rotation with the angle theta 2, it is equivalent to a single rotation with theta 1 plus theta 2. So, the ordering does not matter, you could have done theta 2 first and theta 1. Okay. So, this is an exception in this whole set. Okay. Yeah, but there is a very nice nice fact. Okay. Consider let us consider a d by d antisymmetric matrix okay, and let us consider look at this particular matrix e power a. So, you may wonder, some of you may not know what this means. Another way of seeing this is just to think of this as the following: use the definition of the exponential okay, and you can convince yourself that convergence etc. goes through for this. It is a convergent series, and so you can see that this is actually this has proper meaning. But now comes the interesting thing: you go ahead and take the transpose of this object. It is an easy thing to show. If you come here, it would looking at the right hand side, that it corresponds to taking the transpose of each of these guys, but since it is antisymmetric, A transpose is minus of A. So, you can show that this is equal to e power A transpose, which is equal to e power minus A. What this means is that e power A for any d by d antisymmetric matrix is orthogonal, because what we get is e power A times e power A transpose is equal to e power A into e power minus A, which is the inverse of these things. Okay. But I should caution you that in general okay, while this is true for simple exponentials, this is not true okay, when A B do not commute with each other. That is A B minus B A, but however any matrix commutes with itself. However, when A and B is equal to 0, then you can show okay. So, in this case, in this instance, I can use that formula. Okay. Do you know there is a formula which gives what it should be, that has a name? Does anybody know what that is? It is called the Bch formula. So, there is something called the Baker Campbell Hausdorff formula, which you can look it up, or we will discuss it later in this course, but I would recommend that you look it up and see what it is. Okay, it's given in terms of an infinite series. I sort of remember a bit of it. It's an infinite series. Okay, so but coming back to what we want to prove is we don't have to worry about that issue. All we need to do is we have things which are commuting, so we can use this formula. So what we find is that a large class of orthogonal matrices actually can be realized this way. Now the question is, how large is this class? Before we do anything, one more thing we can ask is, what is the determinant of an exponential? Okay. So I will not prove it, but I will write it out as a claim. Is equal to e power trace of A. For any A, it need not be antisymmetric, but what is the trace? For us, A is antisymmetric. So trace of an antisymmetric matrix is 0. So for when A is antisymmetric, so we can say a little bit more. We can say that e power A is an SOD matrix, not a OD, generic OD matrix, because determinant is +1. So it implies that e power A belongs to SOD. So this is the nice fact which you can actually check. But what makes it really neat is all SOD matrices can be written in terms of e power A in this form. Okay, so in fact as e power A for some A. And this is related to the theory of Lie groups and Lie algebras. This is something which we will come back later in the course, but this is just to show you at least one part of the story you can check, that is e power A gives you an SOD matrix. So it is a non trivial statement to say what the other part, that all SOD matrices can be written this way. SOD, it is not OD, because OD has matrices which have determinant -1, but this will definitely not, I mean. Okay. So now we are kind of ready to define what we mean by a vector of SOD. Okay, it is like chicken and egg. We started out with something and we go back, and we will see that that will let us generalize in a nice manner. Okay, so we will redefine now what is a vector, okay, of SOD. Okay, so answer, it is a D tuple, it is any D tuple that transforms as follows under SOD transformations. Okay, so you just write it out, V prime 1, V2. No, I just write it in short. So it would be V prime I equal to, okay, let's use this notation which we used before, R I J V j. Of course, j runs, I and j run from 1 to d. Okay. So, this is the definition of a SOD vector, okay, and R belongs to so if you put d equal to 3, we recover what we would have meant, what we would have written for normal rotations. Okay. See, the way of looking at this way of looking at it already, even for SOD, lets you write more general objects which transform in a more general manner. And now I want to emphasize that if you find that there is some equation which has which when you say is there is manifestly SOD invariant, okay, let us say it is a vector of SOD. So, some equation okay, so let us say that there is some equation which I will write, which is of the form E sub I equal to 0. So, it is a bunch of D equations, each of which is a vector. So, just as an example would be something like this. Okay, I have written Newton's laws by taking Fi to the other side for I equal to 1 to 3. This would be an example of, so E1 would be m d square x1 by dt square minus F1, E2 would be so on and so forth. The advantage of saying that this is a vector equation and is that under this transformation, that equation itself transforms this way. So, E I would go, E prime I would be whatever it is, it would be R I j E j. Now, if we are given that E j equal to 0 and all these E primes are just linear combinations specified by the entries in the rotation matrix. So, if E j is 0, it necessarily follows that E I is 0. There is nothing to check. The key point here is that this is just a linear transformation. Okay. So, because of that, anything you do, moving things left, right, and things, it does not matter, everything holds. And so that is what one means, that if you write your equations in a form in a form like this and say that this is an SOD vector, you are saying a lot. Okay. And in some sense, this step should be sort of done in your head, not something which you should do again and again, because what we will find later is that we will replace this SOD with something else. And but we will say that but we will nevertheless write some set of equations like this and say it transforms like this. And the most important thing is that if something is a 0 vector in one thing, it will remain it will always remain a 0 vector. Quite often you will see some things in certain examples, you will see where if you it is something is 0 in some frame, if you make a change of frame, it is non-zero. That is sort of the first hint that that is not an object which transforms nicely. In general, in GR, for instance, there is something called the Christoffel symbols. They vanish in some coordinate systems, they do not vanish in another coordinate system. So, that cannot be a tensor or a vector or whatever. Okay. So, we can now, we are sort of ready to define what we mean by vectors, by tensors I mean. Yes.
When you say it's a vector of SOD, could it be
Yes, that is what I will replace the group later, but even within even if we keep SOD fixed, we will see that we can replace the word vector with something else. Okay, so but if you want to keep vector, yes, you can keep vector, but you can replace SOD with this thing. So 4 vectors we saw would correspond to replacing the rotation group with the Lorentz group, but this it is the same story, except the group is the Lorentz group.
That's because the Lorentz group contains rotation.
No, it is a different group, we will see. Okay. Yeah, I mean it is not, enough to say that it is invariant under rotations, that trivially followed. We need not have done all that rewriting in the last lecture, all we because we need to prove that it is invariant under Lorentz boosts. What we will see is that we can repackage Lorentz boosts to look a little bit more like rotations, but it is not quite rotations. Yeah.
When we write these equations and look at manifest invariants, do we look only at rotations or all the symmetries of the coordinates that?
Yeah. So the thing is that it depends on how you write it. So you could have some of the symmetries manifest, some may not be manifest. Going back to Maxwell's equations, the way we started out last lecture, it was manifestly invariant under rotations, because it was either a vector equation or a scalar equation, okay, the set of equations, but it was not obvious how it transformed under Lorentz boosts, or even the fact that it is non-invariant under Galilean boosts. I mean, it does not seem so obvious. So in fact, given a vector, we can construct other objects which transform in more complicated ways, but still the most important thing that would be preserved is linearity. So in one frame you have these set of components, in another frame you get something which is a linear combination of the other guys. Okay, so we want to preserve that. So we will say that a tensor of rank n let us call it some object which has n indices transforms. So tensor now of SOD. So I1, I2, In, each one of these take d values, transforms as follows. Okay. So this looks very complicated, but the transformation law is actually very simple. You sort of close the thing, forget about the fact that there are these other indices J2 to Jn, focus on J1, okay, and see where J1 comes. Here it comes with this, and there is I1, the first index here. We are not at this point looking at these guys. You can see that this index J1 or I1 here behaves like it is a vector. Okay, but similarly I can repeat, forget about J1, now think about J2, same thing is happening out here. So it has a bunch of n indices, each of which transforms like a vector. Okay, so this is the defining property. There are, you can see here that there are n copies of this R matrix, but there is only one T out here still. So at the end of the day it is still a linear combination, it is linear in T, it preserves that important property. So again you get a nice statement, if, which is generalization of that thing, if something is a tensor and it vanishes in one frame, it will vanish in all frames. So again if you write an equation as a tensorial equation, then you are guaranteed that if it is 0 in one frame, every equation you can readjust it and rewrite it as some tensor equal to 0, which is a statement that it is 0 in some frame, it will remain 0 in the other frames. does not matter how complicated these guys are. Okay. Mathematically this is a statement that this matrix R can be written as some tensor, called the outer product or whatever, R tensor R so many n times. If you do not know this, it is okay, but this is what you need. Okay. So, let us sort of take the example of a rank 2 tensor, because we can be a little bit more explicit. So, let us consider a rank 2 tensor. Okay. I am just rewriting this. Okay. And just for simplicity, let us restrict D to be 3. Okay. Now comes the neat stuff. So, this will typical tensor here, I1 can take 3 values, I2 can take 3 values. So, the total number of components would be 9. Okay. So, we can rewrite this transformation as follows. I could just go ahead and write it like this: T11, T12, T13, T31, so on so forth up to T33. I write it as a column vector which has 9 components, and there exists a 3 by 3 matrix, a 9 by 9 matrix, which can be worked out based on this, which will, this is some 9 by 9 matrix, which I will crudely write, which I will indicate as the matrix given by R tensor R, and but this is just explicitly stating that it is a linear change of variables. That means it can be written, this thing in index notation what we have can be rewritten as a 9 by 9 matrix acting on a 9 vector. Okay. So, mathematically this matrix is called R tensor R, but at the end of the day you can see this what is written out here is not the most general 9 by 9 matrix. Its entries are completely determined by this 3 by 3 matrix which you started out with. So, it is not the most arbitrary thing. So, there could be special components which do not mix with each other. Here the way I have written it, it looks like T1 T prime 1 1 will be some linear combination of all these 9 guys. Okay. The answer is that actually that is not true. If you, but there exists a nice redefinition. So, we do not have to write it in this form. There exists a different way of organizing these 9 components such that this R by R takes a special block diagonal form, many zeros come. Okay. And the way to see that is to look at, consider a situation where consider a tensor, second rank tensor that satisfies this condition T I1 I2 plus eta minus eta I2 I1 equal to 0, and eta is either, if it is plus 1 it is a statement that it is a symmetric tensor. Okay. That this is symmetric, and eta equal to minus 1 is antisymmetric. Okay. So, there are two ways of looking at it. One way is to say that fine, this is this is an equation satisfied by this in one frame, it has to hold in all frames because it is just a linear transformation. In other words, if if eta is plus 1, okay, that would say that this is a symmetric matrix. So, T is a symmetric matrix, but what about T prime? It will remain symmetric, that is what this says. You can go back and prove it, you can go back to this definition, but it is better than this particular way of writing it. You can check it. If T is symmetric in two indices, any two actually, okay, let us say it is I1 and I7 or something, it is symmetric under the exchange, this will also continue to hold that, any pair, okay. But since there are only two things, so okay, so now you can see that so what this implies is that instead of doing something like this, if you give me an arbitrary matrix, symmetric matrix, arbitrary second rank tensor, I can break it up into two parts, okay. So any second rank tensor can be decomposed into, so let us write T I1 I2, a symmetric part and an anti-symmetric part. Okay. If we take this 9 by 9 example, how many symmetric guy would have? 3 into 4 by 2, 6 components. This will have 6 components and this will have 3 components for D equal to 3. And the most important thing is that this decomposition does not, I mean it continues to hold. If it the symmetric under rotations, the symmetric part will never mix with the antisymmetric part under rotations or SOD transformations. Okay. So, in particular if you go back there, what one sees is that if you break it up like this. So, if I now write it as S11, S12, S13, S22, S23, S33, these are the, okay. It is simple to write out the expression. So, S I1 I2 will be T I1 I2 plus T I2 I1 divided by 2, the other one would be with the opposite sign. I leave it as an exercise for you to show that, and if I write it out like this, A12, A13 and A23. So, this is like a change of basis if you wish, if you think of this as a vector, just some linear combination acting on that. Then if you work out how it transforms, you will find that you will get a 0 here, which would be how many rows? 6 by 3, and this would be a 3 by 6 0, and these would be non-zero, non-trivial entries, S prime 1 1, so on and so forth till S prime 3 3, A prime 1 2, A prime 1 3, A prime 2 3. Okay. So, you can see the fact that they do not mix with each other is indicated through these zeros. It does not matter what the rotation matrix is, and that just follows from the simple intuitive identification that if something is 0 in one frame, it will remain 0 in all frames. I am just extending it. Okay. In fact, there is something little bit more you can show. This is not the end of the story. You can show that even this breaks up into a 5 and a 1, 5 in the sense that there is a trace of it behaves like a scalar. Okay. So, exercise again. Show that an SO3 scalar. Okay. So, you can break this up into a symmetric traceless part, a trace part, and this thing. Okay. So, there is something interesting which happens in 3 dimensions. An antisymmetric second rank tensor has 3 components, which has exactly the number of components as a vector. This is special to 3 dimensions. So, usually one converts this into another vector. using the Levi-Civita tensor. Okay. But this is a very important point, that actually even though I have written it out in this way, there are parts of it which do not mix. Okay. So what one means is, so the question is, can I do better than this? Already I said first I have shown you 6 and 3, it seems very easy, but I said there is 5 also breaks into 5 plus 1. You may wonder, is there some other, can I make any more changes to make it further smaller blocks? Okay, the answer, and the blocks should hold for all rotation matrices, not one particular rotation matrix. For a given rotation matrix you can always go to some basis where it is diagonal or whatever, and then it will be very simple, but we mean for all rotations it has to be in this block diagonal form, and the answer is that this is it for this example. This breaks up into the trace part, and true for all SOD, not just d equal to 3. So the idea is, so you term that you say that it is irreducible. We will see this again, but it is useful to see it in the simplest example which you actually have implicitly seen. You want to break it up into irreducible components which do not mix under. Okay. So for instance, this 3 by 3 block is irreducible, you cannot break it up any further. Okay. And the statement here is that this 6 by 6 block is reducible into one block of 5 by 5 and another block of 1 by 1. Okay. Are there any questions? Okay. So in the next 5-10 minutes I will spend some time going back on, so far if you noticed I have restricted myself to the special orthogonal part, but there is also the orthogonal part, I mean with the things which have determinant -1, such as the parity transformation. Okay. And what that does for you is to add extra transformations if you wish. Okay. So let us consider parity, and I will define parity not as inversion of all coordinates, I will define an operation P to be, if you wish, the matrix -1 1 1 1 1. So acting on, what do I mean by that? I mean V prime 1 okay. This is obviously, this has two properties, determinant of P equal to -1 and P square equal to +1, it squares to 1. Okay. Since P square squares to 1, it implies its eigenvalues are either +1 or -1. Okay. So this lets you distinguish. So if you give me a scalar under SOD, okay, we break it up into two parts. I am specifying here the eigenvalue of P. If it breaks up into P equal to +1, we call this a real scalar, but it could change sign, and we will call that a pseudo scalar. And anything which transforms like this we will call, so any vector this, we will call it a polar vector. Okay. Because this is changing sign, but an axial vector does not transform under P. So V prime 1 would be 1, but for rotations the rest of the SOD it will transform exactly, they transform the same, but it is how they transform under P that they differ. Okay. So, examples of this, so let us now fix d equal to 3. Okay. So, I need examples of scalars Can you give me examples so that I can write them? Scalars, mass, charge density, charge. What about pseudo scalars? Box product of 3, that is not a scalar. Box product is what? A, oh okay, oh okay. You are saying something like this: A dot B cross C, where A, B, C are all polar vectors. Okay. We will add a few more examples. What about normal polar vectors? Rotation angle, I do not know, displacement would be an momentum, what about electric or magnetic field? Do you know what they are? What is axial? Angular momentum is an example of an axial vector. Okay, fine. Axial vectors. Which is just r cross p. So, in fact, cross product of any two polar vectors is an axial vector. Okay. Exercise for you, go back and check Maxwell's equations are consistent with E being a polar vector and B being an axial vector. So, I can do something simpler than this. I can write E dot B right. Are there any other axial vectors? But most of the examples of axial vectors you start off like this. So, but now the thing is, how do you go about making these assignments? Okay, so the way it is done is, let us talk of the electric field and the magnetic field. You take you start with Maxwell's equations, and first thing we saw that charge was a scalar. So, you look at the equation del dot E equal to 4 pi rho. So, this is right hand side is a scalar, not a pseudo scalar, it is a scalar, and this you can convince yourself del operator is also an axial vector, no polar vectors. So, this if this so now it forces E to be a polar vector. If this were axial vector, this has to be that. Then you go back and look at the next equation, del cross E plus dB by dt equal to 0, I guess 1 by C. So, now this is this thing, now you can see cross product, it forces B to be. So, the point here is that you can go ahead and ask, can I make assignments how they transform under parity by looking at these equations, and that is how you go about doing things. Okay. So, force has to be a polar vector. Okay. So, you can see that you do worry about the orthogonal, the full orthogonal group, but you separate out the part, you separate out the part which is the special orthogonal with respect, and the part of the orthogonal group which is not special orthogonal, and it is just one element, because every other element you can convince yourself that any determinant -1 matrix can be written as P times a special orthogonal matrix. It is not very hard. Okay. The way to see it is that if you give me a matrix O such that determinant O equal to -1, consider the matrix PO. Yeah, this will be an orthogonal matrix. P square is 1 anyway. So, okay, so you can see that it is unique.